Next topic, Young's modulus. Come on. Stuck. We'll just wait. Give it a minute. Maybe I need to close it and open it. Whoop. Whoop. There we go. Okay, Young's modulus. You got that? Yeah. Right, so to start, we have a little bit of vocabulary to do first. So our first word is deformation. Wait, before you write it down, does anyone know this word? You know it, Hareen. What does it mean?
Deformed, which means it goes out of shape.
Yeah, it's like to change the shape. So the deformation of a material is the process of changing the shape, usually the length, for us, of a material. And how do you usually change it, Hareen?
Compressing?
Yeah, by using a force to change the shape, which we call a stressing force. Okay, so write this down now. Over in. How was Lisa's birthday party?
Okay.
It was last Friday, wasn't it?
Yeah.
Yeah. 3 o'clock?
4 o'clock.
Ah, yeah. Now you know why I know, don't you? Because I had low attendance for my class at that time. And then somebody said, "Oh, Lisa's having a birthday party, and all of intake 2 is invited." I'm like, "Oh, okay. Interesting information." So at least, I hope at least it was a good party.
Yeah, a lot of cake.
Good.
Cake involved.
Good. Cake is good. And what did you buy her? You did get her a present, didn't you?
A dress and a necklace.
The classic.
Yeah.
So how many people were there? Estimate.
About 12 to 15.
Okay. Any of the engineers, or were they not invited?
Andy.
Alright. Not the other engineers?
I invited them, but
They were studying. Yeah?
No.
Okay, you got this? Yeah. Okay. Right, so you notice I used the word stress. So we have stress in English. What does stress mean in English? I know you know, but what about you, Trey? What does stress mean in English?
Just stress.
Yeah, what does stress mean? Just in English.
When you feel uncomfortable.
Yeah, feel uncomfortable, lots of work, difficult, yeah? So, in physics we say the stress on a material is the force per area. So it's a lot like a pressure. So as a formula, the stress is force over area. Therefore, the unit is, what's the unit for stress?
PM.
Pascals, yeah.
force per meter squared.
Newton per meter squared, yeah. Yeah, got that? So can you see that's really just like a pressure stress? Okay. Next one. The strain on a material is the change in the length proportionally, which I call x, or sometimes I call x delta x if it's small. And here we call L the natural length. So the strain is how much of the extension divided by the natural length. So it's a proportion, how much the shape has changed. That's an L, natural length. Yeah? Got that? L, yeah? Natural length, the original length. The extension, the delta x. Yeah? Yeah, x is the extension, the change. You got that? Yeah? Continue? Great? Yeah, okay. So the units, can you see that there's no units for strain? You see that? There are no units for strain. Okay. Now, I think I use the letter Y, but I think a lot of books use the letter E, but I don't like using the letter E because I want to keep that for energy. So I'll use Y. Young's modulus is the ratio of stress to strain. So in other words, Young's modulus is stress divided by strain. Yep. Okay. Continue. And what are the units for Young's modulus? Try again. Anybody? The units? Pascals, because the unit for stress is pascals and the unit for strain, well, it's unit 3. The unit for Y? Pascals. Okay. More vocabulary. Tensile strength is a measurement of the force required to pull something such as a rope, a wire, or a structural beam to the point where it breaks. In other words, is how much force you need to break something. Got that? Yeah. Yeah. So for example, let's see, is there anything in this room? If you wanted to break this, the force you need to use to break it, that's called the tensile strength. So this is important in engineering. When you want to build something, you need to know what the tensile strength is for building something. I don't think there's much else to say about that. Right, let's have a look at a graph of stress against strain. Okay, so let me draw the graph here. So let's say you have something, I don't know, I'll do purple. So this is a piece of steel, and what you do is you put some weights on it. So first you put a small weight, then you put a bigger weight, then you have a bigger weight. So these are forces here, like F1, F2, F3. And when you put the weights on them, what will happen is this will become a little bit bigger. So if you have more weight, what should happen to this? Should be bigger, right? Until it breaks. So which is the thing that you're changing, the stress or the strain? So just remember that stress is force over area. And by the way, if I draw this in 3 dimensions, the area is this area here, the cross-section area. Stress is force over area, and strain is the extension over the length. So which one do you change and which one do you measure? So which one do you change? The stress or the strain? No, this is the one you change. You are changing the F. So this goes on the x-axis and this one goes on the y-axis. This is what you see after, and this is what you change. So your graph goes like this: stress, strain. So what shape do you think it will be? Linear. Will it pass through 0? Yeah. No stress, no force means no extension. So you've got a graph that goes like this. Until it breaks. So I don't know what happens when it breaks. It goes funny. When it breaks, I suppose this increases to infinity when it breaks. You know, so if it's being pulled and then it breaks, I suppose the delta x goes to infinity. So I guess the graph, I don't know, maybe it shoots upwards like this when it breaks. Anyways, let's have a look at what the slope represents. So the slope is the strain over the stress. Which is, what's strain over stress? Is the opposite of Young's modulus. So this is 1 over Young's modulus. So then Young's modulus is 1 over the slope. Let me just go back. I'm stupid. No, I'm not stupid. Am I? No, I'm not. Okay. Continue? Yeah. So if you were doing this experiment, I feel like you should put stress on the x-axis because that's the thing you're changing. Yeah? Okay. However, if you put it the other way around, if you put strain here and stress here, you get the same shape, but this time, what does the slope equal?
1.
Yeah, this time it would be stress over strain, which is Young's modulus. In the exam, it depends on the question. So if you're changing the weights, you should put stress on the x-axis. But if you're changing the extension, you should put strain on the x-axis. Yeah, so like for example, if you change this and then you measure this, so this is, you change this, then here you're changing the stress. So you draw this. But the other way you could do it is like this. Let me put a line here. I'll try it again. Can I go down a little? Maybe this time. Sorry, hang on. Alright, it doesn't matter. Maybe this time what you have here, I think you might remember this one, Grace, Amanda and Sophie. Do you remember this, where it tells you the force on it in newtons and you pull it? Yeah? So you could have something here that tells you the force in newtons, and then here you could have your material and then you can pull it. So you change this and then you can measure the force. So if you do it this way around, you should put here the one where you change the strain, and here goes the stress. Now, the one that they usually want you to do in the exam, I'd say 90% of the time it's this one and 10% of the time it's this one. So if they ask you to draw a graph, I don't think it matters too much, but I think it's better if you draw this one, because it's usually like this. Continue? Yep. Actually, let's try and see if there's anything else we can simplify with Young's modulus. So Young's modulus is stress over strain, which is force over area over extension over natural length. But you could use Hooke's law, F equals K delta X. So you could simplify this to K delta X over A over delta X over L, which would be K over A over 1 over L, which would be K times L over A.
What is this? 1?
1, yeah.
1 over L.
Yeah. Now, does the L change?
No.
No. And does the area change?
No.
No. So, Young's modulus and the K from Hooke's law, they're almost the same thing. The only difference is Young's modulus is L over A times K. Or if you want, K is A over L times Young's modulus. That they're nearly the same. So in other words, if this is big, then the Young's modulus will be big as well, and if they're small, the other one will be small. So do you remember what a big K means? If the K is really big, what does that mean about the springs, the material? It's hard to compress it. Likewise, if the Young's modulus is very big, then it makes it hard to compress or pull it as well. In fact, if the area was 1 and the natural length was 1, then you can see that they're the same. But usually the area is very small and the L is very big, usually. So this makes Young's modulus actually a big constant in its number value. We'll have a look at some values now. Okay, continue. Yep. So let's have a look at some constants for Young's modulus. Right, so the first material is rubber. 0.1 times 10 to the 9 pascals, that's rubber. So you'll need these values here. Got that? Continue? Yep, okay. Do you know what nylon is? No?
They used to make clothes sometimes in grass.
Yeah. Grace, Amanda and Sophie, you should know what nylon is. You know nylon? You know nylon? No. It's what you make the tights out of, isn't it? You probably don't wear tights.
No. I guess.
You guess?
Yes. The material to make clothes. Oh,
For the tights.
I guess right.
Yeah. But you probably don't wear dresses, no? No, so you don't wear tights? No. So you know this material is very stretchy. Yeah? What's it in Chinese? Nylon?
Nylon.
Yeah, so it's nearly the same, yeah. So it's very stretchy. 2 times 10 to the 9. So in fact these are small values. Okay, these are small values. You got this? Next, wood. Now you see this is much bigger. 10 times 10 to the 9. Yeah, stress over strain, yeah. And it's a bit like a K. Alright. Glass is even bigger because you can't really pull glass. You know, you can break it, but you can't really pull it. So it's 70 times 10 to the 9. Yeah? Yes? Okay. Brass is a type of metal. What is brass? Bronze and copper, is it? Bronze and... Is it bronze and copper? I don't know. Anyways, brass is a type of metal. It's a very cheap metal. And it's quite large also. Is there any yeah, brass would be like this. This is probably brass, this metal. It's very cheap metal. Copper is even bigger, 117 times 10 to the 9. Yeah?
This is the form until like it gives me a...
No, this is Young's modulus, so it tells us how stretchy the material is.
So the bigger the number, the less stretch.
Yeah, yeah. The bigger the number, the more force you would need to move the same extension. Steel, 200 times 10 to the 9. Now that last one might surprise you. You know graphene? Graphite? Yeah. That's a bit surprising. It's really big compared to the others. Oh, I thought I had one more. No, I don't. That's all of them. Okay, you got that table? Yeah? Okay. Let's have a look at an example. Right, can you write this? Let's do what we've got. We've got 2 examples. Okay. Write this down, so. Let's just say by how much has the wire extended. Yep. Yeah? Yeah. Okay. Let's have a look at this one now. This is the type of questions you might get in the exam on this. Right. So firstly, the boy hangs. Oh, it's a copper wire, and he hangs a weight at the end of it. How big is the weight? It's 0.1 kilograms, isn't it? So the force here is 0.1 G. So there's an up force in the wire as well. What's my first question? Oh, do I tell you how much it extends by? Do I tell you the delta x?
No.
I don't? What do I tell you?
The
Oh, I tell you that's copper, isn't it?
you said it's copper and the wire is 2 millimeters thick.
Right, so what's the first question then?
What is the cross-sectional area?
Okay, so the first one is what's the area. So here's the area here. So what's the formula for the area?
Pi
Pi
r squared.
r squared. Yeah. And what is the radius?
0.002.
2 millimeters?
Yeah, it's 2 millimeters.
2 times, now that's the diameter.
Oh, right. So it's 0.001.
Yeah, because in the question here, I tell you that it's 2 millimeters thick. 2 millimeter wire. So the area is 3.14, yeah, 142 times 10 to the minus 6 meters squared. Okay, Harry, what's the B part? Yep.
What is the stress on the wire?
Okay, what's the formula for stress? Force over area. So 0.1 G over 3.142 times 10 to the minus 6. So that's 312.262 pascals is the stress. Yep. Okay, continue. C. What's next?
What is the strain?
Strain. So the strain is the extension over the natural length. Do we know the natural length? No. Do we know the extension? Do we?
No.
We do not know it. Do I tell you it? No. So instead of using this, we won't use this one. Instead we'll use Young's modulus is stress over strain instead. So then stress is Young's modulus multiplied by strain. Sorry, no, that's not what I meant. I meant to say strain is stress divided by Young's modulus. Now, what is Young's modulus for copper? What's it for copper? In the table. 117 10 power 6. Yeah? 10 power 9? Okay. So then this is 2.669 times 10 to the minus 6 is the strain. Because we know this and we know this now. Yeah? What's the D part? When you're ready.
How much is the nearest?
So what's the delta x then? So we can use the formula delta x equals strain multiply L. Whoa, too far. Oh, do I tell you the length? I think I said 1.5, was it? Yeah. So that is 4 times 10 to the minus 6 meters. Oh, well, if you want, that's 4 micrometers is the answer. So the copper moves only a little bit. Yeah, here it's this one for strain multiply 1.5. Yeah. Huh? No, 2.669 times 10 to the minus 6 is the strain. Multiply 1.5. Makes 4 times 10 to the minus 6. Doesn't it? I think. Well, actually, I don't know either. Yeah, 4.0035. Yeah. Continue. Oh, another part, sorry. E. What's the stiffness constant? What's the K? Alright, so what formula could we use to get K? Well, we could use Hooke's law. Or there's another formula I know. So Hooke's law, F equals K delta X. So K equals F over delta X, which is 0.1 G over 4 times 10 to the minus 6. So that is 245,250 newtons per meter. Yeah? Continue? No? Okay. Yes, Amanda? Yep. Okay, next question. Let me just check what the homework's like. Okay. Right, write this one down. So I want you to try this one before I do it, because I don't think this is too difficult of a lesson, I hope, maybe. So when you're ready, I'll just draw it for you so you know what it's like. I'll just draw the picture. I'll go back to this, don't worry. I just want to draw the picture for you. So in this one, what you have is 4 beams. 1, 2, rough, ugly, ugly, ugly. Ugly. You get the idea. So this is hanging from the ceiling, and what happens is this, I think I said, is how much? 3,000 kilograms, and then here I'll draw a nice big weight of 1,000 kilograms, and this causes an extension of 2 millimeters from the ceiling. So the picture is, it's like this, and it extends down by 2 millimeters in total. So this and this together cause this. That's the picture. Okay, so can you try this now before I do it? Will I go back to the slide? Or you want to look at my beautiful picture? Beautiful picture, okay. Did you write the question down? Okay, so you can try it now. Yes. Here's the question. You don't want my beautiful picture, do you? Which part are you writing down? Last part, okay. Yep, there's the picture again. Oh, wait, hang on. Hang on, both of you need different things. You got it? Okay, and there's the picture. Okay. How are we doing with this?
To get the area, right?
Yeah.
You can take 2 times 2, so you get 4 centimeters, and then you change it to.
Oh goodness no. Change it to meters first, then get it. How are we doing for this one? Do you know what to do?
Maybe.
Maybe. You got an idea, Sophie? So the first part is what's the strain. So the formula for strain is force over area. So the area is these squares. So there's 1, 2, 3, 4 squares, and the square is 2 by 2. The strain, the force is the weight, 4,000 G. So if we go back here, it'll be 4,000 G divided by 4 times 0.02 squared. Is that okay? Yeah. And then the stress, you can use for the stress, you can use this formula to get the stress, because you know this, and you now know this, so now you can get the stress then. Yeah? How are we doing up here now? You're getting the strain? Sorry, do I ask you for stress or strain first? Oh, sorry. I asked you for strain first, not stress. I got confused. So strain is the other formula. This one here. So you know the delta x is this, and the original natural length is this. That's 2 meters. Oh, there. 2 meters, yeah. Let's see how you do. There it is. 2 millimeters. 2 mm. Mm. Delta x. 2 meters. Look. cm. So this is 2m. Yeah.
Oh, each beam.
Yeah.
Take the total strain
And divide by 4. So you do total and divide by 4. Or you can do this number divided by 4 to get 1. Whatever. Yeah. Huh? The length is 2 meters at the start.
The Young's modulus of the material will always be the same, right?
It's a constant, yeah. You could use, oh, the area is the area just here, 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 and here, the 4 squares. You're finished, Irene? Will we have a look at it now? So what was the first question?
The strain.
Yeah, so this here, it was 2 meters, and then it extended a little bit by 2 millimeters. So, firstly we want the strain. What's the formula for strain?
Delta x over length.
Delta x over natural length. 0.002 over 2. What's that?
1 times 10 to the power of negative 3.
Yeah. Okay, what's part B?
No, but the one from each.
Oh, for each.
Yeah.
So then that means the strain would be 1 over 4 times 10 to the minus 3. No. Wait. No. It is this. We don't divide by 4 here, because if we were just looking at one of them.
No, it's 1 times. Oh wait, yeah. Then.
What was the length of this beam at the start?
2 meters.
And how much did it extend by? 2 millimeters, because they all did. Yeah, no, there's no. For this one, it's no dividing by 4. It's for the strain, when the force is shared, we have to divide by 4.
So
What? Yeah?
the strain is just 1 times 10 to the power of negative 3.
Yeah.
No, then everything else is.
That's right, everything's wrong now. What's part B? Stress. Stress is force over area. Now, really, that's going to be the weight divided by 4 over the area. So, Amanda, I think it's fine. What you did was, you did the weight here, and then you divided by 4, was it? Yeah. For me, I'm going to divide by 4 here. Okay, so what is the weight? Is it 3,000? 4,000. 4,000 G. That's the total weight, including the platform, is 3,000.
picture.
I don't understand my picture. But it's a beautiful picture.
Yeah,
Yeah.
no, that's
Oh, that's okay. You understand now it's 4,000 G.
No.
No.
Why is it so?
Well, what's making this pull down? It's this and this together.
What is what's one?
My picture's so bad. Look, what you have here, this part is 3,000 and this part is 1,000. So in total, there's 4,000 pulling down in total. It's like,
Something everything?
yeah, something, let me get this here. So this is 3,000 and this is hanging from the ceiling, and also then there's 1,000 on top as well. So total 4,000. Yeah? Okay. Now the area, so there's 4 areas here. So that's 4 times 0.02 squared. Okay. (6131250) pascals. C is Young's modulus, which is stress over strain. Which is 6131 megapascals.
Maybe the question the answer is wrong.
Oh no! It may be.
But that's what I got. That's all.
I think I'm right. Yes. I feel I'm right.
Yes.
Oh.
Go back.
Yeah.
Yes, okay. Right, let's see.
Wait.
Oh.
6131
Mega,
is
10 to the 6.
It's 4,000 G divided by
Yeah.
4 is equals
Oh, thank you. I made a mistake. I understand now. Yes, you're right. That's I shouldn't have the 4 here. That's what you're going to ask me, isn't it? Yeah. Sorry, I confused myself. Here I'm doing for each, and here what was I doing? The total. So no 4 here. So Amanda, you were right.
Yeah.
This is wrong, but I think you had a different reason maybe.
Because I calculated differently.
Yes, you did it. Yeah, I'm so sorry. So I fix here
Ah.
24. Not 24. I'll put in the total. 24525000 pascals. I'll tell you my mistake. Here I divide by 4, the weight. So here I was doing it for each. But here I was multiplying for 4, means I was doing it for the total. This was wrong. I should do it for each and for each, or for total and for total. Let me explain. When Amanda did it, she did 1, 2, 3, 4. Amanda did the total weight divided by the total area. So she had 4,000 G divided by 4A, because there was 4 areas here. And then when she got her answer, that was for the total, and then she divided by 4 to get one of them. What I was trying to do, which I screwed up, I was going to do the weight for 1 divided by the area for 1. So that would have been 4000 G divided by 4 over one of the areas. And we both should get the same answer. No? Yes? No?
But this is not for each though. This is for
Yeah, it's for
everything.
each.
The 2, 4, 5, 2, 5.
Yeah, this is for each. Yeah. And then I need to multiply it by 4 to get the total. No, I don't need to. Do I ask for each or for total?
Each.
I ask for each. Yeah, well then this is it.
That's it.
That's for each of them. Each of these have this.
But I got that by taking the total.
And divide by 4.
Divided by the area of all 4.
Yeah, yeah.
Then you get each.
No, that sounds like total.
Yeah.
Yeah, but then you need to divide your answer by 4.
Then
You did the total force.
Then you take the 2, 4, 5, 2, 5, 0, 0 divided by 4.
No. What did you do? Did you do the total force?
I took the total.
Oh wait, give me yes no.
Yeah.
Total force
Yeah.
divided by total area.
Yeah.
That gives you total
That
strain.
that
Wait. That gives you total strain.
Yeah.
Yes. Then your answer you divide by 4 to give you for each one. That should be the same as that.
But the total force I got is that. The
No,
2,
no,
4,
no.
5, 2, 5, 0, 0, 0.
No. You had 4000 G divided by 0.02 squared.
Yeah, 0.02 squared times 4.
Times 4. Yes, let me see. Oh, this is going bad. 4000 G. Correct, yeah. Oh. No, I see, I understand. Oh. Now I'm confused. I understand your confusion. Yes. Silly me. Okay, so the reason we have the same answer is the same reason that we had the same answer at the start. That the stress and the strain, it doesn't matter if you look at one part of the total, you get the same answer because it's force per area. How can I explain?
Because the force is also divided by 4.
Yeah. Silly me. Can you look up? Sorry, I'm causing confusion. Oh my goodness. Are we ready?
Yeah.
Yes, okay. Sorry, I'm causing confusion, so I understand Hareen's question now. Hareen wanted to know why was his answer the same as my answer, because he did total and I did for each. Yeah, and the reason is, if you think about it like this, let's say this force here is 2F, okay? And this here is 2A. So what's 2F divided by 2A? Is F over A. Now if you only look at one piece, how much force do I have? 1F, and how much area? 1A. So the strain is also F over A. So in fact, it didn't matter if I looked at the total for 4 or just for 1, we get the same answer. And that's why it's the same. Okay, so I'm sorry, I said you should divide your answer by 4. No, don't. It was right. You got this number also. Okay. Messy, I know. Right, last part. So C, I'll check. I need to fix it. Because we changed the part B. Okay. 2,4,5,2,500 divided by 10 power minus 3. So the answer here is 2,453 megapascals. Okay, last part D. What is the extension if I put on an extra 1000? So you have f equals k delta x. So delta x equals f over k. Do we know the f? Yes. It's going to be 5000 g over k. Do we know the k? No. But we can get it because we know Young's modulus. Do you remember earlier I said Young's modulus, k is, I don't remember what I said.
1 over.
I gave you a formula earlier. No, I'll rework it out. Young's modulus is stress over strain.
It's area over length times y.
Oh, sure, I'm nearly finished now. K delta x over A over delta x over L, they cancel. L over A times K. So K equals A over L times Young's modulus. Did you not write down earlier? Okay. This formula is not in the formula book, so you will need to, work it out anyways. What's the natural length? 2. And then the area? 0.02 squared. Yeah. Can I go back? Yeah. Right, so this will be 5000 G over, what was my formula? L over A times Young's modulus. Thank you. A over, are you sure?
Yeah.
For K? Alright. 5000 G . Zero 0.099979. Okay, so that would be 0.1 meter. So that's 10 centimeters. But earlier, how much did it 2 millimeters? Oh, that's a big difference. Or if you want, that's 100 millimeters. So that's an extra. Wow.
Why?
Yeah? Extra 98 millimeters. No. I'm not, it seems so big. Yeah. No, I'm pretty sure. Pretty sure, yeah.
What is the area?
Now for this one, the area is for one of them. Divide by 4. 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 So that is 2.5 centimeters, which is 25 millimeters. So that's an extra Okay, this seems better. 23 millimeters. Disgraceful. What a mess. Oh well. It's the end of the chapter.
The area is 0.02 multiplied by 0.02.
Yeah, for this last part we must do it for one because the K is only for one beam. It's like one string. So here, this last piece we think about as like one, string, rubber string.
So these two are not connected.
Yeah. Okay, can I close this? Give you the homework? Yes? Okay.
What is the L?
2
Meaning
meters.
meter.
Meters, yeah. Finished? Got the picture? Right, so the plan is for Thursday we'll do the tutorial and then we'll do practice presentations for Hareen, Amanda, Grace and Sophie. I'll have the projector. Do you want to bring your laptop or do you just want to use my laptop?
Your laptop.
Then you need to email me your presentation so I can save it on the desktop. You know my email. We know.
I mean, I might know.
Perhaps it could be Stephen at
Yeah.
DIFCDublin.ie.
Okay.